So getting into the one-sided limits out of the way, and then it was piecewise continuous, and so it's integrable according to these piecewise functions that each have, that are tractable to integration, that have a closed form for integration and computation of the pre-derivative or the antiderivative with respect to the integral, and that being according to the FTC and such. Another type of integrable function frequently used in applications is described in a later exercise. The function f from the unit interval to r, defined by f of x equals sine 1 over x, is bounded and continuous and therefore integrable on 0, 1. It's not defined what it is from 1 over 0. And because sine is defined for the entire range of x, it is just somewhere out there on it in the periodic in 2 pi. But it is not piecewise continuous because f of 0 from the right does not exist. So that's just an example, of course. So I think that the notions of the piecewise continuous in the functions and the continuous in the functions and the Riemann integrable are pretty familiar to everybody because that was the course. That was what was called calculus back then. And when we learned the fundamental theorems of calculus and how to arrive at computing s for the limit, first of all the derivative and then the integral, and various means that were shown to demonstrate how to construct the various, according to the various rules, the various forms and the integrals, and usually after that they had a reverse operation from the derivative, which is always nice. And so stepping down or stepping up the values that became multipliers, and otherwise after the power law, pretty much the power rule, getting up into these other forms, and that for sine and cosine, they're reflective about sine and negative cosine, and cosine and negative sine, and these sorts of things, and then the various forms which result for the product rule and the quotient rule, if that being just a product rule under quotients, and the substitution of variables and this and that and the other things. That the author gets into some examples of, for example, functions that are defined piecewise but over different parts of the domain, that adds discontinuities, and the removable discontinuities. There is that after we learned the derivations, then there are many exercises to follow, and usual exercises and forms. That often enough the identities and these kinds of things that became useful for finding identities or mapping forms and integrating or computing integrals and derivatives and searching for them and finding in them how to make manipulations that result in arrive at closed forms. Those are often provided and made clear which ones would be most useful. The author defines a geometric series. Since the sum of the geometric series on the right, with sum n equals 1 to infinity of 1/2 n, is known to be 1, this total length is e, an arbitrarily large number. And so that gets into the notion back into the idea of, well, if they're removable discontinuities and they're arbitrarily small, that we can still use it for analysis. Now, this reminds one of the discussion from the path integral, and also from the PDE work, and there's when these approximations kind of get built up, or these forms when there's assignments. And it's not an abuse of the notation so much as that it reflects, though, that it is a purposeful assignment to say that there's sometimes when removable discontinuities exist, and that it's still integrable as like this other kind of function, that as well, if there's any kind of condition that blows those up, thus that they gain arbitrarily larger analytical character than their arbitrarily small analytical character, then it's possible then they have arbitrarily measurable analytical character. And those are exactly the kinds of things that go into what are the dynamics of when the regime of the differentiation or integration on either side is one way or the other, and then the getting from either side to the other side is dynamics in how it goes. Riemann's 1854 paper also contains, as an application of his new definition of the integral, a very powerful result which will serve us well later on. In its simplest form, it says that the Fourier coefficients approach 0 as n goes to infinity. This should be clear from the graphical representations and the interpretation of integral and area. As area, and basically has that most of them will be as of the integral. As I consult back to the definitions, most of them will be as the integral of cosine x nx cosine mx, fx sine x, and fx cosine x. Well, I'm not really sure how to have it for so, except that I'm not really sure that's so, because, but it is kind of clear, it should be equally clear that the interval negative pi to pi and the positive integer n can be replaced by an arbitrary interval ab and an arbitrary positive real number r. Moreover, in 1903, Lebesgue proved that the result is still valid using a broader, more powerful definition integral that he had introduced himself the previous year. This gives the theorem its present name. The Riemann-Lebesgue theorem. If f is integrable on AB, then these quantities are equal and equal 0. The limit as r goes to infinity of the integral from a to b of fx sine rx dx equals the limit as r goes to infinity of the integral a to b fx cosine rx dx. I'm not so sure of that, because cosine rx is periodic, and between a and b it'll mostly range between 0 and 1, but also cosine of rx for it just means that between some arbitrarily larger a and b that will range between 0 and 1. I mean, if a and b are between negative pi and pi, it would be one thing, but here it's I don't really understand why this is so yet. And here's the proof. Let A equals between x naught and xn, inclusive, an ordered array of partitions, be a partition of A, B, and if m sub I is the largest real number that is no larger than any value of f on a partition, such a number is called the infimum of f on this partition. Define G from AB down to R by G of x equals m sub I for x in that partition, and G of x sub I equals f of x sub I equals 1 through n. Clearly, G is less than equal to f on AB, because the m sub I is not larger. Then it takes the integral of from a to b of fx sine rx dx minus the integral of a b gx sine rx dx, so it makes that smaller than the integral of a b fx sine rx minus gx sine rx. That absolute value, all in quantity dx, implies less than equal to integral a b fx minus gx dx, integral to f integral of a b fx dx minus the sum I equals 1 to n of m sub I x sub I minus x sub I minus 1. So it's sort of having made that for each of these partitions, that it just eliminates that part from the this, and then the idea is that it goes to 0 is just kind of the same as the definition of the Riemann integration. But what don't really get is that it's assumed that the assignment of the validity or the equality is in effect to make that so the claim. So in this theory of Fourier series, now we've got two different assigned things, and we figure that each one is no different, and that neither one of them blows up. So in this sense, there's the idea that why it doesn't seem so very fulfilling, the Riemann-Lebesgue theorem, is that it's a result in the Riemann-Lebesgue theorem. And so outside of it, about purely the analytical character itself of the sinusoidal functions, at any particular, and the partitions can be arbitrarily contrived, and the steepness of these of the one partition to another can be arbitrarily large, and so even though one of these elementary functions one of these elements of the series is like so, it's kind of making the case that they all would add up to be like so, when otherwise it's arguably that there's a particular other way to look at this that makes for a conjecture, if later shown false, any mistakes are my own, a conjecture that there are exceptions to the Riemann-Lebesgue theorem. And it gets in the definitions of functions, the definition of integrable, the definition of the Fourier series and its coefficients, and the equations of it. It gets into all such sorts of things, and the fact that that otherwise it's very very exact, and it would be so that it's just saying that it's Riemann integrable, and so that as that goes to zero, then also these would go to zero. So this limit only exists in Riemann integrated areas, and so it has to go hand in hand with the following further development of this to be accepted, because otherwise it's just like the above assignment again about when the removable discontinuity is negligible, because it's not generally so, it seems, that it would be zero, their difference. Besides that one or the other would be less than or equal to the other, the inequality, that it's not necessarily an equality. Okay, so going on, it says then, what does it say? By definition 2.2, given epsilon greater than 0, the partition can be chosen so fine, well here he goes kind of develop it, that the right hand side is smaller than epsilon over 2, and then using the inequality x is less than or equal to y plus x minus y, valid for any real numbers x and y, and then so he just frames the strict inequality in terms of the difference between that and epsilon over 2 is arbitrarily small number. And he says, but for r greater than 0, integral from a to b of gx sine rx dx equals sum I equals 1 to n of these partitions, each integrated piecewise, equals the sum of these mi over r times cosine r xi minus 1 plus cosine r xi, or taking the definite integral, and is less than or equal to 2 over r, I equals 1 to n of the absolute values of m sub I. For r large enough, the right hand side is smaller than epsilon over 2. for r large enough. And then the integral is less than the integral of from a to b of fx sine rx dx equals epsilon for such large r. Since epsilon is arbitrarily small, the first limit follows, and the second is obtained in an analogous manner, quod erat demonstrandum. The QED stands for it is proven, quad, what was commenced, what was stated, is erat demonstrandum, demonstrated. Well, all right, then to carry on with that, that's an analytical framework about establishing for the Riemann-Lebesgue theorem that in the signal continuity and signal analysis, if things are to be going on in the dynamics of that somewhere, or when something starts to blow up, what happens when it does? These are the kinds of things to figure out. Section 2.4. Back in 1829, Dirichlet had proved that the Fourier series of a bounded function f that has a finite number of jump discontinuities and a finite number of maxima and minima on negative pi pi converges to f at every point x at which f is continuous. Yeah, this is the most amazing thing, that you can add up all these multiples of scales of these functions and add them up to what's there. And it's so amazing for anything that can be sort of the basis for things, that if you can find a way to write any function in terms of any other function, and it's not something that I ever had really a great facility in, but I really like to study the fundamentals to understand about like these orthogonal functions and the ideas of how to go about deriving that it's so that they do add up according to some arbitrary coefficients, that you can take any given function and build it in a given region as an infinite many, or sometimes when it's smooth about it, and it's closed for the differential geometry, these submersions and immersions, the idea of getting a finite series in these basis functions or these elementary functions of it, that the Fourier series is real great. And because first of all, everybody had a lot of facility with trigonometry back in 1777 and 1894, 1829. And they had a lot of other very usual and regular properties, and they were computed to a great extent. And then the idea of being able to work up these kinds of things and getting stuff out that you only need the first so many terms, and that'll give you most of the character, as we've just kind of shown by the Riemann-Lebesgue theorem. Well, it's not really so in the nonlinear. It's not so, but it's so here in the close and the small and the near and the dear. So converges to fx at every point at which f is continuous. In 1854, Riemann discovered that the convergence of such a Fourier series depends exclusively on the values of f on an arbitrarily small interval centered at x, a fact usually referred to as Riemann's localization principle. Well, I don't know why that's any different, because but it seems kind of contrived to be about the intermediate value theorem, and it's probably built about the same way as the previous result, the Riemann-Lebesgue theorem, and because that's pretty much his rule, is to set up for the infimum, and then just take that down to 0, and then express it in terms of epsilon, that he's kept as a constant across the way. Here's a nice picture of Dirichlet, portrait by Schrader, photographed by the author from Dirichlet's Mathematische Werke of 1889. So we shall combine these two results into a single convergence theorem, and the use of the Riemann-Lebesgue theorem will allow us to give a shorter and far more palatable proof than the original one by Dirichlet. It may be shorter and more palatable, and when it's deconstructed, almost necessarily it would get larger and more verbose. And there's not necessarily anything wrong with that, because then it's possible to be express enough that it's formalized how there are differences in dynamics and these kinds of things. The first step is to rewrite an arbitrary partial sum of its Fourier series. That is, s sub n of x equals the Fourier series, where n greater than or equal to 1 is arbitrary as an integral whose limit is later found as n goes to infinity. It's like a Fourier series, but just with n instead of infinity. Using the definition of Fourier coefficients, he's just written out the computation for the Fourier coefficients, and then having sums instead of the integral that forms the coefficients. To form the nth or mth coefficient, instead of it being an integral. Oh, he has this production of the, how do you say, coefficients inside the integral, otherwise of this coefficients. So that he has 1/2 pi times quantity integral from negative pi to pi of ft plus dt plus 1/pi. So I suppose since dt is closed, that integral, it's a totally separate expression. Sum from 1 to n of this bracketed term cosine nx integral negative pi to pi ft cosine nt dt plus sine x nx integral negative pi to pi ft sine nt dt. So equals 1/2 pi integral from negative pi to pi ft bracketed quantity 1 plus 2 times n plus 1 to the n equals 1 to the n sum cosine quantity n times quantity t minus x, that bracketed quantity dt. Both Fourier and Dirichlet proceeded in this manner, and then each chose a certain trigonometric identity to compute the sum in the square brackets on the right. But Dirichlet's choice of trigonometric identity, namely 2 cosine nt sine 1/2 t equals sine n plus 1/2 quantity t minus sine n minus 1/2 quantity t, resulted in a better simplification of the integrand above, making it easier, in fact possible, to find its limit as n goes to infinity. Adding the equations that result from substituting n equals 1 through n in the previous identity, we obtain 2 sine 1/2 t times the quantity sum from 1 to n of cosine nt equals negative sine 1/2 t plus sine quantity n plus 1/2 t. Hence, if t is between negative pi and pi and not equal to 0, we have that 1 plus 2 times n plus 1 to the n cosine nt equals this quantity sine of n plus 1/2 times t and over sine 1/2 t. And that as n goes to infinity, or rather as t goes to 0 here, and as t goes to 0, the right hand side has a limit 2n plus 1, which is precisely the value of the left hand side for t equals 0. And the right hand side is piecewise continuous, and since the previous identity is equally valid with t minus x in place of t, we obtain an integral in ft dt times this term that's in sine of the large number plus 1/2 times quantity t minus x and sine 1/2 t minus x, which should be the same thing as 1. This is the first result obtained by Dirichlet. We can simplify the notation by defining d sub n of t equals that term that reduces, which is called the Dirichlet kernel. Now I was thinking that this would be as to where the I would just double everything, because then that would be just 1. which is called the Dirichlet kernel, if we use it to rewrite 5 and 6, and if we observe that integrating the left-hand side of 5 from 0 to pi yields the value pi, then we can sum up the results obtained so far as follows. Let it be so, then the Dirichlet kernel, then the integral from 0 to pi of dn of the Dirichlet kernel dt equals pi, which is the same as the integral of 1 dt equals pi. And as sub n of x equals 1 over 2 pi, integral of negative pi to pi ft dn of t minus x dt. So this Dirichlet kernel is kind of contrived, and it's basically about the periodic properties of this function, and then as to why it cancels out, and it's about symmetry and about also the period of the function. Is kind of only for a large value, because it's got to be a large enough value that's bigger enough than x, that otherwise it wouldn't be a whole many more extra periods of this periodic function for it to be so that this Dirichlet kernel falls out. So if otherwise, that this n, if x is arbitrarily large and close to n, then it would not be so. It would not be so. And so for this integrable function, there's this Dirichlet kernel's integral is it's b minus a from integral from 0 to b, or the integral from 0 to pi of Dirichlet kernel of t of dt equals pi. And the Sn of x equals 1 over 2 pi, integral from negative pi to pi, ft, and then dn t minus x dt. And the author writes, since the statement of this lemma may look a bit technical and unexciting, we shall illustrate its importance and that of the Dirichlet kernel by some intuitive remarks, which actually form the basis of the convergence proof. Or where it's not. For n large enough, the graph of d sub n, quantity t minus x versus t, is represented in a figure. Its zeros are the points t equals x plus k delta, where k is a non-zero integer and delta equals 2 pi over the quantity 2n plus 1. So this is about the however many periods there are of this periodic sinusoidal function, or the zeros is how many of those there are. And for very large n, we can think of the main arch in the graph of d sub n t minus x as a quasi-triangular window resting on the interval x minus delta x plus delta, through which we can see a very narrow portion of the graph of f, also represented in figure 2.4 for a continuous function. As x varies, the window moves, revealing only values of f very close to fx. When the product ft d sub n t minus x is integrated from negative pi to pi, as required by equation 8, the representation of the figure suggests we can neglect contribution to the integral from outside the interval. That's really the convergence part, is that there's all this stuff left out on the outside of it. And so when x is arbitrarily large, then that goes out the window. Inside this interval, ft is approximately fx, while the area under the main arch in the graph of dn t minus x is approximately delta 2n plus 1 equals 2 pi. Then that second lemma, as it were, from the definition of s sub n of x, or the series, which is mostly about it's integral from negative pi to pi of ft times sine of a really large number and t minus x, and whether x is a really large number or it's not, over sine 1/2, which is just a given point of this quantity t minus x, and whether x is the s sub n is x is the x series element, and integrating that with respect to dt, that it's a very large offset to build this out this sort of window, and so this convergence effect is much similar to the it's establishing convergence criterion. So of course it's much similar to the Gauss-Lebesgue theorem, or establishing an inequality that becomes strict and then becomes zero, and this to epsilon, or an arbitrarily small thing. But here it's making an arbitrarily large enough thing that for this 2 pi, this implies that s sub n at x is approximately equal 1 over 2 pi of x minus delta to x plus delta ft times the Dirichlet kernel of t minus x dt is approximately equal to f of x over 2 pi the integral from x minus delta to x plus delta of Dirichlet kernel of t minus x to dt is approximately equal to fx for n very large. So when I think of this, it harkens me back to the idea of the hat series, because I want to figure out how to write another kinds of these series, just to show as a model and a toy that it's possible to make up another kind of these things that has the same properties, and that there's a world of them if you can find what to look for, and all this kinds of thing. So the idea is that if the hyperbola is 1 over x, so the reciprocal function, after this identity dimension, that you can kind of shrink things down from it in terms of that, and so it ends up looking like a triangle, ends up looking kind of like or the sawtooth wave with the triangular sawtooth wave. So you flip that over and then add up these functions to make it like so, instead of the sine and cosine there, but there's otherwise these orthogonal functions, because it's to be made so that they have whatever it makes it so that they have these various parts that come and go in the analysis from left to right in the plane, or as about the polar, or circular, or about developing some integration formula just for this identity dimension and down in that, and having those halves or either side of that being symmetrical and so on, building out this whatever it needs to be that it so results. Then in an analog to each of these results of Riemann and Lebesgue and Dirichlet, and for Fourier and after Euler, the idea is just to build it down from that to arrive at then these same kinds of results, which results is sort of a contrived but limited in applicability, but smaller and that's faster, a means to compute for positive numbers, or what can be written in these forms, these kinds of things, and then to get other usual systems of well-known things in terms of that, and then just build it outside the box and make that an adapter regularly available to the rest of analysis. These are the kinds of things that go in the idea of trying to improve mathematics while still keeping it possible to have it be self-contained, and even simply related. So these are nice things. ... for n very large, and so these various proofs of convergence kind of build up to where there's an arbitrarily large quantity, and so something else would be small, arbitrarily small and go to zero, the differences, or there's an arbitrarily small quantity, and for these arbitrary quantities that the differences would be less than it, large and small. Then the non-standard is that it's truly infinite. How does it work? Or it's truly infinitesimal. That's because it was truly infinite too. These are the kinds of things it gets into. Hence, it is reasonable to expect that s sub n at x goes to fx as n goes to infinity, as is our wish to prove. It is reasonable. Now, in these non-standard forms, there are cases where it's not. But here it's kind of that they collapse together, they sandwich together, they kind of they combine together. It's reasonable to expect this. Moreover, this approximation suggests that if the right-hand side has a limit as n goes to infinity, then both this limit and the convergence of the series S of n of x at a given point x depend exclusively on the values of f on the interval x minus delta x plus delta, which becomes arbitrarily small as n goes to infinity. This is establishing for convergence that in this interval, then the series exists and perfectly reconstructs the symbol. Now it's kind of like this sampling theorem, which is what? Which is, well, if you have a particular sinusoidal function and you want to reconstruct it, if you can oversample it at twice its frequency, then you can construct its value. Sample reconstruction. And so that's a particular thing for a particularly simple thing already, but it's only about one of its own kind that it can double up and make up for itself the same thing. Compared to this is that for an arbitrary function, you can have an infinite series of these coefficients as applied to each of these functions, as applied to each of these multipliers that add up. Back to the thing. It will be easier to state and prove the convergence theorem if f is extended beyond the interval negative pi to pi as a periodic function of period 2 pi. This will simplify the computations, and of course it does not alter its Fourier series on negative pi to pi, since the coefficients are still evaluated as integrals from negative pi to pi. While that's so, it's like if you were to have to, every time you wanted to use the result, you'd have to prove the convergence theorem first. It gets into the cases in S where x is large compared to n. If the region became arbitrarily large compared to the original proof, you'd essentially have to recompute it in terms of an arbitrarily larger number than that. So depending upon how such things are symbolized, or represented in the declaration or expression of this kind of proof. And for example, it's like, well, we're actually not even using infinity. We're just using an arbitrarily large finite number, and it's still pretty close. Given the precision of the differences that we maintain anyways, in some fixed point numbers or something. It would have to be re-derived. Or there's the dynamic says about it that make it so when it would start to let out, when it would start to get fuzzy, when it could blow up, or simply become dissonant in a sense, or disappear. It will be easier to state and prove the convergence theorem. In fact, you can luckily we can just treat those as symbolic and arbitrary quantities and express on the outset of it that when you say n is arbitrarily large, it is, even if you come back later with the larger or the other numbers, it's still just arbitrarily large. And ditto with the epsilon, it's just arbitrarily small. And so it'd have to be always kind of left that way, as in its nature and its elements, sort of a infinitesimal or an infinity. This was called the infinitesimal analysis. In fact, if f is extended as stated above, making the change u equals x minus t from the series definition with the Dirichlet kernel, and noticing that the Dirichlet kernel is an even function, we obtain the series x equals negative 1 over 2 pi integral from x plus pi to x minus pi f of x minus u, which is f of negative t, but after replacement like so. Dirichlet kernel of negative u du equals 1 over 2 pi integral from x minus pi to x plus pi of f of quantity x minus u d sub n u du. Since the integrand is now periodic of period 2 pi, the integral has the same value over any other interval of length 2 pi. And so it reduces like to so that the series is 1 over 2 pi integral from negative pi to pi instead of, x minus pi and x plus pi. That same term. In a similar way, but making the change u equals t minus x, we would obtain s sub n of x 1 over 2 pi integral from negative pi to pi f of x plus u d sub n of positive u du. Adding the last two equations, observing that the resulting integrand in brackets f of x plus u plus f of x minus u. So you kind of building up similarly as for orthogonal functions that this x squared minus 1 results kind of a thing, but that these come down as about the even and odd functions, times dnu is an even function of u, and replacing u by t, and this gets back into the whole, how about x equals t, that's kind of, well, it's still square because they're each other. It's like the small angle approximation that sine theta equals theta. At the limits, at the extremes, when there's not enough precision otherwise to keep it all together, because there's not infinite precision. But there is mathematically, but when there isn't, we arrive at this series is equal to 1 over 2 pi, integral from 0 to pi, so having that, because we've got a doubling form about it, fx plus t, f of x minus t, times Dirichlet kernel t dt. Before we state the convergence theorem, we need to impose a differentiability requirement on the function f. To this end, we recall the following concept. It's piecewise continuous, and then about the right-hand derivative, then left-hand derivative. And the second limit definition can be written as about the even and odd functions, fx minus h minus fx minus. The fact that we shall use, it's differentiable, and its right and left hand definitions and derivatives exist and are equal. In a piecewise continuous function, the left and right derivatives don't necessarily equal, because you can imagine like it's a straight line from the left and its derivative is 0, and its identity to the right and its derivative is 1. They're not equal. If this limit exists, and so he just takes the derivative from the right. Well, okay. And then he gives an example from negative 1 to 1. This function is piecewise continuous, and its right-hand and left-hand derivatives at x equals r are 0 and 1/2. All right, yeah, that's fine. But the piecewise continuous functions always have one-sided limits at each point. That's the definition that's continuous, that a function is continuous at a point. Lemma, if f and f prime are both piecewise continuous on a closed interval a, b, then f has one-sided derivatives at every point x in a, b. Only one, of course, at each endpoint, and they're equal to the one-sided limits of f prime at x. That's fine. If x is not equal to b, and if f is not continuous at x, then there is a number h greater than 0 so small that f is continuous on x, x plus h, and f prime is continuous on x, x plus h. By the mean value theorem, there's a point C between x and x plus h, thus that for the finite difference fx plus h minus fx from the right over h equals f prime c. It's because it would cross it somewhere. As h greater than 0, h goes to 0, we see that c goes to x and f prime c goes to f prime x from the right. Hence, the previous equation shows that f has a right-hand derivative and its value is dot dot dot. Similarly, if x was a, then dot dot. So that lemma is shown. Now, and it goes on, it says, we are now ready to state and prove the convergence theorem of Dirichlet and Riemann. And so we've kind of already gotten into the existence of the integrability of it for this convergence of the Fourier series and other systems of series that are to show that they exist and make a convergence to any function that's continuous or otherwise well-defined in a way for our means of integration. Because it's possible that this is only like 10 theorems deep to build a entire apparatus to make a system, an analytical system for these things, that then you call any function in that space a product of these elementary pieces that add up to it, which is kind of nice. In a bounded region. It's generally that in a bounded region is so. And so it might work out for something like when the space is already sort of a bounded region, it might make it easier to at least fill that out to the edges. These are the kinds of things I think about when I want to add something to mathematics. Which is probably already very well explored. So, looking forward to Dirichlet and Riemann, they're going to prove that the series converges. Let a function from R to R be a periodic function, a period 2 pi, there's usually a notion for periodic functions that their period is a constant, and that it's modular in this sense, just like this semicircle wave can be, if the semicircle wave is drawn by a segment of length 1/2, then the period would be 1. And every 2 revolutions, 2 half revolutions it does to make a revolution, it would increment 1. It's constant. But then the idea of that, if that segment, the inchworm or whatever, every revolution grew or shrank, is the idea of then such otherwise these modular functions that kind of just work out being in the lattice of the zeros of the functions that are the wave functions of these things. I'm just expressing that this kind of condition is very regular, and then makes it really simple to keep things all squashed out because it's regular in dispersion on the way out to that. Okay. That is integrable on negative pi to pi. Then its Fourier series on negative pi to pi converges to the value 1/2 of the quantity f of x plus f of x minus at every point in x and r such that f has right-hand and left-hand derivatives at x and such that f is piecewise continuous on an arbitrarily small interval centered at x. If, in addition, f is continuous at x, then its Fourier series converges to f of x. So it's saying that the Fourier series is kind of interesting and nice, that when the function is piecewise continuous, it might have a kind of a vertical line between it. See, now I've been thinking of piecewise continuous in that its derivative was piecewise continuous. And so it's kind of describing it that if it's discontinuous but still Riemann integrable, because it's like a block and then a block too high or whatever, so that the function would basically be connected by a vertical line, that the Fourier series adds up to the average of those, 1/2 of the left and the right hand side. Which when they meet and they're the same, then of course that's no different than the one, but the average of twice the number is itself. Excuse me, the half of twice the number is itself. But all right, that just is to just advise what was previously mentioned about the piecewise and continuous and dot 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 and the Fourier series and the demands of Riemann integrability, because it allows there to just be Riemann sums of Riemann regions. And in that for Lebesgue, they're basically just horizontal instead of vertical. And still teases either. At every point x and r such that f has right-hand and left-hand derivatives at x and such that f is piecewise continuous on an arbitrarily small interval centered at x. If in addition f is continuous at x, then its Fourier series converges to f of x. So that's the theorem. Proof. The last statement is obvious from the previous, I suppose. The convergence of Fourier series. Now, if delta less than pi is a positive number so small that f is piecewise continuous on x minus delta, x plus delta, then using 9 and 7, so that would have been the definition of the series, and well, I'm going back a ways here to find this formula. 9 and 7. Here's 2 and 3. Excuse me one moment. 2 and 3. Oh, here we go. That 8 was the series number. 7 was the Dirichlet kernel. Okay. 7 was the Dirichlet kernel, and 9 was the f of x plus t plus f of x minus t. The integral of that times the Dirichlet kernel. Right? In terms, we obtain the series minus 1/2 of f of x from the left plus f of x plus the right. So it equals this 1/2 pi integral from 0 to pi of f of x plus t, f of x minus t minus f of x from the right minus f of x from the left times this quantity dn, the Dirichlet kernel t dt equals 1/pi instead of 1/2 pi, and integral from 0 to delta of this bracketed quantity f of x plus t minus f of x from the right over t plus this quantity f of x minus t minus f of x from the left over t, that quantity bracketed, times 1/2 t over sine 1/2 t times sine n plus 1/2 t dt plus 1/2 pi integral from delta to pi f of x plus t plus f of x minus t minus f of x from the left minus f of x from the right, all that quantity over sine 1/2 t times quantity sine n plus 1/2 t dt. If f has right-hand and left-hand derivatives at x, each quotient in the brackets in the first of the last two integrals on the right has a limit as t goes to 0 from the right. Then the expression in the brackets is a piecewise continuous function of t on 0 delta because f is. The next factor is continuous on 0 delta, and it is well known that this is the small angle approximation limit of 1/2 t over the sine 1/2 t equals 1 as t goes to 0. This is the theta over sine theta. Theta goes, as theta goes to 0, that theta is approximately equal to sine theta. A small angle approximation. Now, this always causes me grief because it's arbitrarily small, and it's an approximation. It's a linearization. It's an approximation. The derivation of that is still kind of it's an issue. It is well known. Thus, this integrand is the product of a piecewise continuous and therefore integrable function by sine of the quantity n plus 1/2, that quantity, which is the same thing as sine plus 1/2 if n is a multiple of 2 pi. That's arbitrarily large. whether it's like a point at infinity that's composite or point at infinity that is prime would make a difference. The quotient in the second integral is integrable on delta pi because both the numerator and the denominator are. As long as the denominator is not 0, of course. Though, that when you think of the integral of something that was differentiated, it's kind of an issue. Therefore, each integrand on the right-hand side is the product of an integrable function by sine n plus 1 half t, and we conclude from the Riemann-Lebesgue theorem that each integral tends to 0 as n goes to infinity. QED. So that establishes that the Fourier series converges even to the discontinuous but piecewise continuous integrable functions of a sort. The remarkable thing is that while the Fourier coefficients that make up the series depend on the values of f over the whole interval negative pi to pi, the convergence of the resulting Fourier series at a given point does not. It is a purely local property due to the fact that for very large n, the main arch in the graph of the Dirichlet kernel is concentrated over a very small interval, while the others are negligible. Huh. Well, that's been pretty interesting. So this is pretty common stuff. And what I mean by that is that oftentimes, and I've sat through class before where I've been instructed in Fourier series and these sorts of results that arrive at how we compute these things and developments and this and that and thereof and therefore. Now I don't really recall this Riemann-Lebesgue convergence by that name, and I don't really recall the Dirichlet-Riemann convergence by that name and the Dirichlet kernel. And I think what I saw was probably a slightly different variation about how some of these things are built up, the existence of the convergence of the series, and then the computation of the values of the series. And so that's something to think out and figure about. And then what goes into it and why it's kind of simple is because it's possible to just carry it out in terms of delta epsilon x. And what would you call it when you just have an arbitrarily large number and then you have something that's regularly periodic, so it's just kind of is treated like an arbitrarily large number divided by that is an arbitrarily small number. It's delta epsilon x again with regards to quotients or inverses. That they so on together build up these notions of the limits and for convergence and then for the analytical character, how to build up for these families of functions according to their other properties, the orthogonality and the normalization, to figure out for these special functions then how to make it so that you can derive the proofs that there exist these combinations that are a space for the values of these functions, their values and variables. And then particularly to figure out then for which one of those kind of grow or shrink, and so then it's possible to assign how to compute these values based on these ones. But I imagine there's a lot more to learn about the applicability of these Fourier series and other kinds of the ideas of the transforms. Because a lot of the ideas of the transforms, like Henkel and Mellon and Z, and all these other transforms, any one of which kind of has an orthogonal function as its basis about this Dirichlet kernel, and that's about that each of these kind of things has for Fourier functions have a Dirichlet kernel, and other ones have their own. That these are the kinds of things that get into what then applies for various things that are more angular than smooth, or is it the way these piecewise things add up together, or that they're smooth and continuous. All these kinds of families of transforms then that for various usual things that they're normally going to integrate to come up with closed forms that were like direct two-step, but then they at least have it in a worst case that they can still compute it and get a right answer. And especially if they can just work as long as they have time and then get as close an answer as they can and don't get a pathological case or a wrong answer. These are the kinds of things. And so even in those few pages, what it shows is after development of conditions for integrability and fundamental theorems thereof, then, as was mentioned, less than 10 theorems deep or whatever, it's possible to build up a scaffold of an apparatus of an analysis and a means. So that was interesting, and I'll consider that as I'm trying to figure out how to get a pretty thorough overview of the methods of analysis and what goes into all the things for this descriptive differential dynamics and the integral calculus as a whole, because I already kind of have the foundations that I've built up from this line continuity, field continuity, and signal continuity. So I fully intend to figure out how to apply that to these all usual things as well as I can and add something to mathematics. And so these are the kinds of things that are ongoing with it. Well, all right then. Hey, have a great day.